Okay, so now let's do one example for vapor power system. The structure is still the same as before. A boiler where you gain heat QH, a steam turbine where you generate work WT, a condenser where you release heat QC, and a pump where you consume work WP. And then on the right hand side, that's the process on the P versus nu diagram. The area of the enclosure is still equal to W cycle per unit mass. What is given is P1 equal to P4 equal to 50 bar. They are equal because you can see on this P versus nu diagram, 4 to 1 is on a horizontal line, so they must have the same y coordinate. So P1 equal to P4. And same reason goes to P2 and P3. They are equal and equal to 5 bar. W122 control volume work per unit mass is equal to 364.31 kilojoule per kilogram. It must be positive because we know 122 is the steam turbine, which generates work. Generating work means the work must be positive. What we're looking for is WCV per unit mass and the Q per unit mass of each process. We need to find those two for 421, 122, 223, and 324 separately. So now let's start from 421 first. Let's write down. This is for process 421. The name of process 421 is isothermal expansion. Okay, so first one, what is the control volume work of 421 per unit mass? The solution is very straightforward. Remember, control volume work, WCV, only comes from moving parts. So 421 is a boiler. Inside a boiler, there's no moving parts. There's only water going through a pipe. There's no moving parts such as blades or piston. So if there's no moving parts, control volume work, WCV, must be 0. And I want to make a note here. Sometimes it can be confusing to you because we know on the P versus nu diagram, if you take a look at the right half of the diagram, we know the area under the curve tells you W per unit mass. And we look at 421. Do we have an area under 421? Yes, we do. So does that mean the work for 421 is not equal to 0? Yes, but the area under the curve is not WCV, but W total, like we explained last time. So remember, area under 421. Area under the curve, let's be general. Under a curve on P versus nu diagram is equal to W per unit mass. That is true. But what kind of W is that? It's W total. It's not WCV. Those two are different for a control volume. So now even though you do have an area under 4 to 1, WCV is still 0. Okay, so now next time when you look for WCV, just keep one thing in mind. Do you have a moving part? If you do, then WCV is not equal to 0. If you do not, then WCV must be 0. Okay, so now that's easy, huh? We just found work. Next one, we're looking for heat transfer. We have work, we're looking for heat transfer. What equation goes to your mind? Yes, first law. And which one? The long one or the short one? Let's take a look. 421 is a boiler. Does it have an inlet and outlet? Yes, you can see you do have inlet and outlet. So this is a control volume. If it is a control volume, you have to use the long version of first law. The long version of first law is Q dot and give it a subscript because this is a process 421 minus W dot 421 control volume work plus M dot inlet is number 4 and the outlet is number 1. right hand side dE over dt. So now let's simplify this equation. Right hand side goes to 0. The reason is it's at steady state. WCV we said must be equal to 0 because there's no moving parts. And then V1, V4, the velocity does not change, so those two terms cancel. Z4 and Z1, the height does not change, so those two terms cancel each other. And then this equation will be simplified to Q dot 421 plus M dot H4 minus H1 is equal to 0. And now we move Q and M to one side. Q dot 421 over M dot is equal to H1 minus H4. Okay, and keep that in mind. What are we looking for? We're looking for Q over M. We're not looking for Q dot over M dot, but they are actually the same. Why? I can prove that. Q dot is defined as Q over time, and M dot is defined as M over time. And then you can see the two t's cancel each other. What is left is just Q 421 over mass, exactly what we're looking for. So now you can see what do we need. We just need H1 and H4. Before you look for properties, you first need to identify what's the phase of the substance. What's the phase at number 1 and number 4? If you forgot, let's go back to the diagram. Number 4 is point F, and number 1 is point G. So now we can just easily go to the table and look for HF, which will be my H4, and Hg, which will be my H1. So now, next question, which table? Do we know the pressure or the temperature of this of point 1 or point 4? We know the pressure. The pressure they have is the same, is 50 bar. If you start from pressure, you go to table A3. We start from pressure. Can be either P1 or P4. They're the same, 50 bar. And then you go to the table, you look for HF and Hg. HF will just be our H4 and Hg will just be our H1. So we copy down those two numbers from the table. 1154.2, don't forget the unit, kilojoule per kilogram. And Hg equal to H1 equal to 2794.3 kilojoule per kilogram. Do not forget a unit. So now we can easily plug in those two numbers and look for Q421 per unit mass. We'll do a plug and check. H1 is 2794.3 minus H4 1154.2. Solution is 1640.1. Unit is kilojoule per kilogram. That is our solution. And now pay attention to the sign to your solution. This is a positive number. Does it make sense to have a positive heat transfer for 421? Yes, because what is 421? 421 is the boiler. That's where your system, which is the water, gains heat. If the system gains heat, heat transfer must be positive. So now we're done with the first one, process 421. We move on to the next process. After 421, let's go to 122, the steam turbine. Process 122, steam turbine. Process 122 has a name. Just you forgot the name is adiabatic expansion. And adiabatic means there's no heat transfer. So let's look for W122 control volume work per unit mass first. What is it? It is actually already given. It's right here, given 364.31 kilojoule per kilogram. So we just copy down this number, 364.31 kilojoule per kilogram, already given. Next one, heat transfer. Heat transfer is even easier. Why? Because from the name, adiabatic, we know there's no heat transfer. If there's no heat transfer, Q122 must be 0. The reason is adiabatic. Doesn't have heat transfer. So process 122 is probably the easiest one we have, huh? Okay, so now we move on to the next process. After 122, the steam turbine, what do we have? We move on to 223, which is the condenser. Okay, so we move on to 223, the condenser. Process 223 has a name. It's isothermal compression. Isothermal means temperature doesn't change. So now let's look for work first. W223 control volume work per unit mass. And what is the control volume work for 223? What is 223? Let's go back. 223 is the condenser. Do we have any moving parts in the condenser? No, we do not have any moving parts. What happens is you just have some pipes, and inside the pipes you have some fluid. The fluid flows by and cools down and loses heat. That's all it does. There's no moving parts like a piston to push or blades to push. So that's why WCV for 223 must be 0. Again, just like 421. If there's no moving parts, WCV must be 0. So now we have work. We're looking for heat transfer. What equation goes to your mind? Yes, first law. So let's start from first law. Q dot, give it a subscript 223 minus W dot 223 control volume work plus mass flow rate. Inlet is number 2. Minus exit. Exit is number 3. And right hand side still the same, dE over dt. So now we do the same. dE over dt goes to 0 because it's still a steady state. WCV is equal to 0, no moving parts. And then this is the change of kinetic energy. There's no change in kinetic energy. Neglect delta KE. We also neglect delta PE because there's no change in height. So same as before. Q dot 223 over M dot is equal to Q 223 over M, and the solution is H3 minus H2. So now we just need to find H2 and H3. Okay, so before you look for properties, like we said, you always need to find out what's the phase of these points. Number 2 and number 3, let's go back to the P versus nu diagram. They are both under the vapor dome, so both of them are mixtures. If you want to look for a property of a mixture, you have to have quality, and we do not have quality. And there's no easy way at this moment for us to find the quality. So we cannot find H2 or H3 because we do not have the quality. We don't have X2 or X3, so we cannot find H2 or H3. If we cannot find H2 or H3, then we cannot find heat transfer for 223. So this method doesn't work. First law doesn't work for this case. So how should we look for heat transfer 223? Don't forget, this is a Carnot cycle. If you see the Carnot, don't forget what's the definition of a Carnot cycle. It's a series of 4 processes, and each one of them is reversible. So if you see the word Carnot, you need to think of the word reversible. And just like we said before, if the process is reversible, what you're going to have is actual efficiency eta must be equal to eta max. This is a hidden equation if you have Carnot cycle. Keep that in mind. Carnot means every step is reversible, and if the process is reversible, eta must be equal to eta max. Okay, let's start from left hand side. Eta. Eta is defined as W cycle over QH. That's the definition of ATEM. And what is ATEM-X? The equation was given, 1 minus Tc over Th. And how do we write W cycle? Do you remember? W cycle can be rewritten to QH minus QC over QH. Right hand side still Tc over Th. Okay, so left hand side becomes 1 minus QC over QH. Right hand side still the same. Okay, so now we can do the algebra. What we will have is actually QC over QH equal to TC over TH. Okay, so next one. Which one is QC? Which step gives you QC? Let's go back to the diagram. QC, losing heat. Which step loses heat? 223. So we can rewrite QC to Q223. And what is Q hot? Q hot is gaining heat. That's in process 421. So we can change QH to Q421. Okay, so we change the subscript. QC, we change it to Q223. And Q hot, we change it to Q421. Right hand side is still TC over TH. Okay, so now what we can do is to move Q223 to the left hand side because that's the one I'm looking for. So right hand side becomes Tc over Th multiplied by Q421. And then one last step, we divide every term by mass. Q223 over mass. And right hand side becomes Tc over Th times Q421 per unit mass. Left hand side is exactly what we're looking for. And now let's take a look at the right hand side. Do we have Q421 per unit mass? Yes, we did find it from part 1. So now if I need to find a solution, I just need to find T cold and T hot. That's the only two I need. Okay, so how do we find T cold and T hot? Let's go back to the P versus nu diagram. T cold is the temperature in the condenser. And you can see T cold is the temperature of this G point. And TH is the temperature in the boiler, and you can see that's the temperature of point 1, which is point G2. And remember the definition of saturated temperature. Saturated temperature is defined as the temperature of point F or point G. T hot is the temperature of point G. Tc is also the temperature of a point G. So both Tc and Th are saturated temperatures. How do you look for saturated temperatures? You can go to the table and start from the pressure and look for the corresponding saturated temperatures. So do we have actually P1? P1 is given, so P1 is 50 bar. We go to table A3. We start from pressure 50 bar, and we look for the corresponding saturated temperature, and that will just be T hot. And then we repeat. We go to table A3. We start from P2, which is 5 bar, and look for the corresponding saturated temperature, and that temperature will just be our Tc. We go to table A3, we start from pressure P1, which is 50 bar. We look for the corresponding saturation temperature in the table, and that is our TH. Solution is 264 Celsius. Then we repeat, go to table A3. This time we start from P3 or P2, that is 5 bar. And then we look for the corresponding saturated temperature from the table, and it is our Tc, which is 151.9 Celsius. So now we can just go back to this equation and plug and chug. So now Q223 per unit mass is equal to Tc over Th times Q421 per unit mass. Tc is 151.9. Make sure you convert it to Kelvin. T hot is 264. Convert it to Kelvin. Multiply by Q421 per unit mass, which we found earlier from part 1. The solution was 1640.1, and the unit is kilojoule per kilogram. So finally, our solution is 1295.7 kilojoule per kilogram. So now 223 heat transfer per unit mass is equal to 1295.7 kilojoule per kilogram. And now let's take a look. 223 is the condenser. Condenser is where you lose heat. If the system loses heat, your heat transfer must be negative. Is our solution negative? Our solution for 223 is positive. How? That's because we didn't use first law of thermodynamics. The signs are very strict you have to follow whenever you use first law of thermodynamics. But when we were looking for Q223, we did not use first law. What did we use? We used Carnot cycle, eta equal to eta max, to find Q223. That's why the solution doesn't have a negative sign. So now if you give me this positive number, it will be correct. But if you add a negative sign to your solution, I will also consider it as correct. Okay, just keep that in mind. If you use first law of thermodynamics, you have to make sure the signs are correct. Okay, so now you can just also add a note. The system loses heat for 223, so you don't forget later on. Okay, so now we're done with work, WCV, and heat transfer for process 223. And then finally, we're moving on to the last process, 324. Process 324 has a name. The name is adiabatic compression. Okay, so work versus heat transfer, which one you think is easier for us to find? Probably heat transfer is easier. Q324 over mass must be equal to 0. Why? Because this process is adiabatic. Adiabatic means no heat transfer. So sometimes if you can remember the name, it's going to make your calculation faster. You don't even need to calculate anything. So now we have heat transfer. I'm looking for work, WCV. What equation goes to your mind? Exactly, first law of thermodynamics. And again, because 324 is the pump, where you have inlet and an outlet, meaning you have heat mass transfer. So it must be a control volume. If it is a control volume, you have to use the long version of first law. Q dot 324 minus W dot 324, control volume work, plus M dot H3 plus 1 over 2 V3 squared plus GZ3, because number 3 is the inlet, and then minus number 4, which is the outlet. Right hand side is still the same, dE over dt. And same as before, right hand side goes to 0 because it is steady state. Q dot 324 must be 0 because there's no heat transfer. Neglect the change of kinetic energy, and also neglect the change of potential energy, just like before. And now, what about W324 CV? Is it equal to 0? 324 is the pump. Do we have moving parts in the pump? Yes, we do. We have some blades, rotational machinery inside the pump to increase the pressure. So that's why this number will never be 0. And also you can think this way. How do you make a pump work? You have to provide the pump with electricity. Providing work, that means what? Your system consumes work. If your system consumes work, this work will not be 0. It will be negative. It will never be 0. Okay, so now we rewrite this equation. into this format, W dot 324 control volume work over M dot is equal to H3 minus H4. And remember, we're looking for W324CV over M without the dots on top of them. And they are just exactly the same. Why? I can prove that. W dot is defined as W divided by time. And M dot is defined as M over time. Those two t's cancel. So what is left is W324 control volume work over M. And that's exactly what I'm looking for. In order for us to find the solution, we need H3 and H4. H3 and H4. What about H4? Do we have H4? We actually have H4 already when we were doing part 1 right here. HF is equal to H4 and the solution is 1154.2. So we actually have H4 already. So we actually have H4. The only thing we need is to find H3. How do we look for H3? We can start from H2 first. And how do we look for H2? We can put it in a process 1 to 2. So let's recall process 1 to 2. And we apply first law to process 1 to 2. The very long version, because process 1 to 2 is the steam turbine, which is a control volume. We apply first law and we simplify first law. What you get is W dot 1 to 2 over M dot and is equal to H1 minus H2. This is what we get. Okay, W dot 1 to 2 control volume work over M dot is given, and H1 is found from earlier. Do you remember what H1 is? H1 is right here. H1 is equal to Hg and is 2794.3. So we do have H1. And now one equation with only one unknown. I can find H2 easily. Alright, so H2 is equal to H1 minus W dot 1 to 2 control volume work over M dot. So we plug in the numbers. H1 is 2794.3 kilojoule per kilogram. Minus second term in the right hand side, W dot 122 control volume work over M. What is it? It is given by the problem. Let's go back. What is it? It's given 364.31. Oh, by the way, so what is given is W over M. What we have in our equation is W dot over M dot, but we know they are equal because the two dots will cancel each other. Okay, so now before you plug in this number, you have to make sure the sign is correct. Like we said, whenever you use first law, you have to double check the sign for work and heat transfer must be correct. So should we plug in a positive 364.31 or a negative 364.31? 122 is the steam turbine, which generates work. If your system generates work, this number must be positive. So that's why we're plugging a positive 364.31. So minus a positive number, 364.31. The unit is also kilojoule per kilogram. So the solution for H2 is 2429.99. The unit is kilojoule per kilogram. This is how you find H2. And now we can find H3 from this H2. How? We can put 2 and 3 into one step. That's process 2 to 3. So now what we do is we recall process 2 to 3 and we apply first law of thermodynamics again for process 2 to 3. Simplify it just like before. What we found from the first law is Q dot 2 to 3 over M dot is equal to H3 minus H2. And we can find H3 from here. H3 is equal to H2 plus Q dot 2 to 3 over M dot. We do have H2. H2 is right here. 2429.99. The unit is kilojoule per kilogram. Next one, plus plus Q dot 223 over M dot. Where is that? We actually found it right here. Q223 per unit mass is equal to 1295.7 kilojoule per kilogram. So one thing is, what we have is Q over M. What we are using in our equation is Q dot over M dot. They are equal because just like before, the two dots can cancel each other. So that's okay. Okay, so don't panic. And next one, before you plug in this 1295.7, we need to double check if we should plug in a positive number or a negative number because we are using first law. And you have to be very strict with the signs when you use first law. 223 is the condenser. That's where you lose heat. If your system loses heat, this heat transfer must be negative. So we should plug in a negative 1295.7. Negative 1295.7, and the unit is kilojoule per kilogram. And I'll make a note here. Don't forget this negative sign, okay? Because 223 loses heat. You have to add this negative sign. All right, and then in your calculator, you can find a solution. It's 1134.29 kilojoule per kilogram. So now we've found H3. Okay, we can go back to our equation. We have H4, we just found H3. We plug in those two numbers, we can look for W324 control volume work per unit mass. W324 control volume work over mass is equal to H3 minus H4. And we just found H3, that's 1134.9 minus H4, which we found earlier, 1154.2. Solution is negative 19.91. Unit is kilojoule per kilogram. And does it make sense for us to have a negative solution to work? Yes, because 324 is the pump. Pump consumes work, so that's why this work must be negative. Okay, so this is the example.